Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on group, lecture number 66, in which I will solve some miscellaneous problems on subgroup, normal subgroup, quotient group and isomorphism theorem. Now we solve some problems. Problem B, let F be a homomorphism defined on a group G onto a group G prime with kernel H. For each subgroup K prime of G prime, define K by K is a subset containing all those elements of G such that Fx belongs to K prime. Then number 1, K is a subgroup of G containing H and K prime is isomorphic to quotient group K by H. Number 2, K prime is a normal subgroup of G prime if and only if K is a normal subgroup of G. Number 3, if K prime is normal in G prime, then quotient group G by K is isomorphic to quotient group G prime by K prime. Number 4, K prime and K is 1-1 correspondence between the set of all subgroups of G prime and set of all subgroups of G which contains H. Now we solve this. Solution. Given that F is a onto homomorphism defined on group G to G prime is onto homomorphism defined on group G to group G prime. Let this is group G and this is group G prime. F be the onto homomorphism with kernel H. That means let EG prime be the identity element of group G prime. Then image of all elements of H be EG prime. This H be the kernel of F. Let K prime is a subgroup of G prime. Then given that K equal to X belongs to G such that Fx belongs to K prime. Now we solve problems one by one. Number 1. Since K be a subset of G, group G. Now let A, B belong to K. Here A, B implies that F A, F B belong to K prime. Since If x belongs to k, then fx belongs to k prime. Since k prime is a subgroup of G prime, implies that FA, FB inverse belongs to K prime, implies that FA, FB inverse belongs to K prime, since F is homomorphism, implies that FAB inverse belongs to K prime, since F is homomorphism. Here FAB inverse belongs to K prime. Here we have seen that fx belongs to K prime, then x belongs to K, implies that AB inverse belongs to K. Therefore, AB belong to K implies that AB inverse belongs to K, implies that K is a subgroup of G. First part proved. Now to show K prime is isomorphic to K by H, quotient group K by H. Since H equal to kernel of F, therefore H, small h belongs to H, implies that FH equal to EG prime. EG prime be the identity element of G prime. Let this is number 1. Since K prime is a subgroup of G prime, therefore identity element EG prime belongs to K prime. This is number 2. From 1 and 2, we get H belongs to capital H, implies that FH equal to EG prime, and EG prime belongs to K prime. Therefore, FH belongs to K prime implies that H belongs to K. Let this is number 3. From 2 and 3, we get H is subset of K. This is number 4. Since K is a subgroup of G, therefore from 4, H is a subgroup of K. Since H equal to kernel of F equal to a normal subgroup of K. Therefore, H is a normal subgroup of K. Therefore, quotient group K by H exists. Let this is group G and this is group G prime. F be the homomorphism, H be the kernel of F, and K be a subgroup of G containing H. Here K prime is a subgroup of G prime. Since F is a homomorphism defined on group G onto G prime, therefore it induces that F is a homomorphism defined on K onto K prime. Since kernel of F equal to H, therefore by fundamental theorem of homomorphism, or first isomorphism theorem, the quotient group K by H is isomorphic to K prime. Here this is K and this is H equal to kernel of F, F, and this is K prime, another subgroup of G prime. F be onto homomorphism. Therefore, the quotient group K by H is isomorphic to K prime. Psi be the isomorphism. Second part of 1 is proved. Now we prove number 2. Let K prime is a normal subgroup of G prime. To show K is a normal subgroup, let X belongs to group G and small k belongs to subgroup K. Now X, K, X inverse. Now we use the function f. This equal to, since f is a homomorphism, therefore this equal to fx, fk, fx inverse, since f is a homomorphism. This equal to fx, fk, fx whole inverse, since f is a homomorphism, so fx inverse equal to fx whole inverse. Let this is number 1. Since x belongs to G, implies that fx belongs to G prime, and k belongs to subgroup K, implies that fk belongs to subgroup K prime, and K prime is a normal subgroup of G prime. Implies that fx, fk, fx whole inverse belongs to K prime. From 1 and 2, we get fx k x inverse belongs to K prime, implies that x k x inverse belongs to K. This is number 3. Therefore, x belongs to group G, small k belongs to subgroup K, and from 3, x k x inverse belongs to K, implies that K is a normal subgroup of G. Proved. Conversely, let K be a normal subgroup of group G. Now, let Y belongs to G prime and small k prime belongs to capital K prime. And since f is on 2, therefore there exists x belongs to G and K belongs to capital K, such that fx equal to y and fk equal to K prime. Let this is number 4. Therefore, y K prime y inverse equal to y means fx, K prime means fk, and this is fx whole inverse. This equal to fx, fk, and this is fx inverse, since f is homomorphism. This equal to fx k x inverse, since f is homomorphism. This is number 5. Since K is a normal subgroup of G, therefore X belongs to G, K belongs to capital K, implies that X, K, X inverse belongs to subgroup K, normal subgroup. Implies that F, X, K, X inverse belongs to K prime. This is number 6. From 5 and 6, we get Y K prime Y inverse belongs to K prime, capital K prime, implies that capital K prime is a normal subgroup of G prime. Proved. Now we solve number 3 to show the quotient group G by K is isomorphic to quotient group since given that K prime is a normal subgroup of G prime, implies that K is a normal subgroup of G from 2. Therefore, quotient group G by K and quotient group exist. Let phi be a mapping defined on group G to group quotient group G prime by K prime such that phi x equal to fx K prime. Let this is number 1. Now to show that phi is a homomorphism, let x, y belong to group G, implies that fx, fy belong to group G prime, implies that fx K
G
prime,
prime by K prime.
fy K prime belong to quotient group G prime by K prime. Also, x, y belongs to group G by closure property. Now, phi xy equal to fxy K prime, and this equal to fx fy K prime, since f is a homomorphism.
G prime by K prime.
So fxy equal to fx fy. This equal to fx k prime fy k prime. Since k prime is a normal subgroup, and this equal to phi x and this equal to phi y. Let this is number 2. Therefore, from 2 we get phi is a homomorphism. This is number 3. Let x prime belongs to G prime implies that x prime k prime belongs to G prime by k prime, and since f is onto, therefore for any x prime belongs to G prime, there exists x belongs to G such that fx equal to x prime. Therefore, for any x prime k prime belongs to quotient group G prime by k prime, there exists x belongs to G such that phi x equal to fx k prime. This equal to x prime k prime. Therefore, phi is onto. This is number 4. Here we have G prime by K prime, and this is group G. For any element x prime K prime belongs to quotient group G prime by K prime, we get a pre-image x in G. This is phi. Therefore, from 3 and 4 we get phi is onto homomorphism. This is number 5. Since K prime be the identity element, this is K prime, now we have to find kernel of phi. Therefore, kernel of phi equal to x belongs to G such that phi x equal to identity element of quotient group G prime by K prime, that is K prime. This equal to x belongs to G such that phi x is fx K prime. This equal to K prime. This is number 6. For
fx k prime equal to k prime implies that fx belongs to k prime, because k prime is a subgroup of G prime. And this means x belongs to k. This is number 7. From 6 and 7 we get kernel of phi equal to
all those elements of group G which belongs to K. That means
car phi equal to k, kernel of phi. This is number 8. From 5 and 8,
in 5, phi is onto homomorphism defined on G into quotient group G prime by K prime,
and kernel of phi is k. Here k equal to kernel of phi. Here quotient group G by car phi of G prime
therefore,
by
from
k
5
prime,
and 8
and using be the identity element of G prime by k prime.
fundamental theorem of homomorphism,
The quotient group G by car phi is isomorphic to quotient group G prime by k prime. G by kernel of phi is isomorphic to G prime by k prime, implies that G by car phi equal to k is isomorphic to G prime by k prime. Proved.
now we prove number 4.
Let k be a subgroup of G containing H and k prime equal to f small k such that k belongs to capital K. Now let small k1, small k2 belong to capital K, implies that fk1, fk2 belong to K prime, since K is a subgroup of G. Therefore, K1, K2 belong to K, implies that K1, K2 inverse belong to K, implies that f K1, K2 inverse belongs to K prime, implies that f K1, f K2 inverse belong to K prime. implies that f k1 f k2 whole inverse belong to k prime, since here f k2 inverse equal to f k2 whole inverse, because f is homomorphism. F is homomorphism. Therefore, K prime is a subgroup of G prime. Now let L is a set containing elements of G such that Fx belongs to K prime. Let this is number 1, this is number 2, and this is number 3. Let Y belongs to H and H is subset of K, implies that Y belongs to K, implies that Fy belongs to K prime. And Fy belongs to K prime, Fx belongs to K prime means X belongs to L, implies that here Y belongs to L. Therefore, H is subset of L. Let this is number 4. Now, let X, Y belong to L, implies that Fx, Fy belong to K prime, and K prime is a subgroup, and since K prime is a subgroup of G prime, implies that Fx, Fy whole inverse belongs to K prime, implies that Fx, Fy inverse belongs to K prime, since here Fy whole inverse equal to Fy inverse, because F is homomorphism, implies that Fxy inverse belongs to K prime, since F is a homomorphism, and this means Fx belongs to K prime, then X belongs to L. This means Xy inverse belongs to L. Therefore, L is a subgroup of G. Now, let small k belongs to capital K, implies that Fk belongs to K prime, and Fk belongs to K prime implies that K belongs to L, implies that K is subset of L. This is number 5. Again, let small l belongs to capital L, implies that Fl belongs to K prime, implies that L belongs to K, implies that L is subset of K. From 5 and 6, we get K equal to L. This is number 7.
Since K prime equal to the elements containing Fk, K belongs to capital K, subgroup K, indicates that a subgroup K of group G containing H has 1-1 correspondence with a subgroup K prime of G prime, and from 7 K equal to L, therefore any subgroup L of G containing H has 1-1 correspondence with a subgroup K prime of G prime. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.